Hi everybody, welcome back. This is Unit 10, Lesson 5, I think. I can't really remember, but I think it's 5. And we're going to talk about equilibrium in this section of our notes. And to kind of explain the idea or the concept behind equilibrium, I have this little faucet or bucket of water here. Okay, this is in section 4 of your notes, okay? We want to talk about what equilibrium is today and the different types of equilibrium. So if you look at this system here on the board, it's not in your notes, but there is water going in, right, to the bucket, and there's water coming out of the bucket. Those are two opposite processes, two opposite things. The one faucet is filling the bucket, and the one faucet is emptying the bucket. So those are two opposite processes. If the rate of water filling the bucket is equivalent to the rate of water leaving the bucket, what do you think will happen to the amount of water in the container? And this is the idea behind equilibrium. We can say actually that this is at equilibrium because the rate of water entering is equal to the rate of water leaving. So do you have a guess what will happen to the amount of water inside the container? You're right if you said it should stay the same. It should remain the same because it's going in as fast as it's coming out. And that's the idea behind equilibrium. Equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. So it doesn't really matter if they're fast or slow, they're proceeding at the same speed. Okay? So some reactions are reversible, meaning they can go both ways. And I have an example of a reversible reaction here on your paper. Okay? In the forward reaction here, hydrogen reacts with oxygen to make water. Forward and energy. Okay, forward would mean it proceeds in the direction as it's written. This is the forward reaction. Okay, it produces a lot of energy, and I'll show you a video of that production in just a minute. If you go in the reverse reaction, well then you're going backwards. You're going this way. You start with water and you put energy in and you break that water down back into hydrogen and oxygen gas. So this is an example of a reaction that would be reversible. Notice the double arrow is what we use to show a reversible reaction. That double arrow can look like that, or sometimes you'll see the double arrow like this. Okay? Or sometimes they'll actually just draw two arrows that look like that. But that represents a reversible reaction. Okay? I have an example of the forward reaction here. A couple years ago, my AP class went to Niagara University, and the professor at Niagara University had two balloons, one filled with hydrogen gas and one filled with oxygen gas. And he caused the two of those to react. So I'll show you that right now here in this video, I think. It's a little dark. Let's back that up a little bit. I don't know if you can see it. It's like very dark. It was a little scary. We did it in the stairwell, as you can hear. What that big flash was that you saw was when the hydrogen reacted with the oxygen, and that represented, that big flash or flame was the energy that they produced. Okay? So you can see the energy that they produced. All right. There are some things that are true at equilibrium. At equilibrium, the concentration of reactants and products do not need to be equal to each other. However, they will remain constant. Okay, just like the amount of water in the bucket remain constant. So my analogy to this is pretend that there's only one bridge here that connects the United States to Canada. And the population of Canada here is what? 1, 2, 3, 4, 5, 6, 7. Let's say 7 million. It's not, but I'm just making it up. And the population, that would be the concentration, right, of people. And the population of the United States is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 million. Okay? That would be the concentration. By the way, I just made that up. That's really not the concentrations. The idea behind equilibrium is that the rate of the forward reaction would equal the rate of the reverse, meaning the rate at which people leave Canada to go into the United States is equal to the rate that the people leave the United States to go into Canada. Okay? And so if that is true, if for every 2 people that leave the U.S. to go to Canada, 2 people leave Canada to go to the United States, what would happen to the amount of people? What would happen to the amount of people in Canada? What would happen to the amount of people in the United States? Again, they would stay the same. Are they equal to each other? No, they're not. There's 7 million here and 14 million there, but they would stay constant over time. So when it comes to equilibrium, you really look for 2 things, okay? You look for, and I know this isn't written down, but 2 things are true at equilibrium. Number 1, there are equal rates. The rate of the forward equals the rate of the reverse. And number 2, there are constant concentrations. Not equal concentrations, constant. Meaning the concentrations don't change, but they don't need to be equal to each other. It's a very important idea. There are 3 different types of equilibrium we have to talk about. The first one is phase equilibrium. Obviously, these exist between different phases of matter as they undergo a phase change. So that would be, for example, when the rate of melting the solid turning into the liquid equals the rate of freezing the liquid turning into the solid. Okay, but again, look at this. Rate equals rate. Rates are equal. Okay? This always occurs at the freezing point for any given substance. And remember, for water, the freezing or melting point is 0 degrees Celsius. So at 0 degrees Celsius, we have a solid-liquid equilibrium. The rate of freezing equals the rate of melting. Okay? On our heating and cooling curves, that represents your first plateau. The rate of freezing equals the rate of melting. Okay? We also have a liquid-gas equilibrium. That would be when the rate of vaporization, liquid turning into gas, is equal to the rate of opposite process, which is condensation. Gas turning into liquid. So that occurs on your second plateau on the curve, right? This is your liquid gas region, okay? And for water, this occurs at a temperature of 100 degrees Celsius. That's the boiling or condensation point of your substance, okay? So this curve that we've learned way back in our very first unit not only tells us where phase changes are occurring, it also tells us where we are in an equilibrium, where processes are occurring at the same rate. EQ for equilibrium. There's a solution equilibrium. What you need to know is that saturated solutions are in equilibrium. And in a saturated solution, the rate of dissolving, which is when a solid turns into an aqueous solution, equals the rate of the reverse process. The rate of the reverse process would be when you're aqueous and you're turning back into solid. We call that crystallization. Again, what's the important point? Well, number 1, saturated solutions are in equilibrium. And again, rate equals rate. It's when the rates of reverse processes are the same. And then finally, our ordinary chemical equilibrium, which is when the rate of the forward reaction equals the rate of the reverse reaction. So there's 3 different types of equilibrium that we will cover in this class. In tomorrow's video, Friday's video for the weekend, we'll be talking about factors that disrupt the equilibrium. And on Monday, we'll do a lab where we investigate those factors. Have a great night, everybody. We'll see you in class tomorrow. Bye-bye.